Okay, the last talk, great responsibility. First of all, thank you for inviting me to this conference. I'm here on behalf of the UCLA Galactic Center group and in particular Andrea Gees, and I will present my own work, which has been published in 2014 on G2, and the work of Brianne Sitarski, who is working on G1 and is about to submit a paper very soon. I think I will have not to introduce a lot about the Galactic Center. At the moment, the beautiful two talks that Stefan gave a very good introduction to G1 and G2 and to the Galactic Center. Let me just say one thing here. I had the privilege to work with the VLT in my career and the Keck telescopes, and it's just fantastic what you can achieve with AO-supported telescopes. And that we can actually see G2 and G1 is not, talk in the way we talk about it, is not only due to the technology and the development of adaptive optics, but also the long time scale that actually these research was committed. It's more than a decade of data we have now accessible, and we can look indeed at the time development of all those sources. Well, the UCLA Galactic Center group has a little different perspective. First of all, data-wise, we heard before that unfortunately NACO was not available during the Periaps passage in 2014, and we decided to concentrate on the continuum observations to complement basically what we can know about G2. And the second part is that we have a slightly different perspective. We still think that the idea that G1 and G2 are of stellar nature is very attractive. And what one has to understand is that all these ideas, what it could be, not only exist due to the observations we have, but also due to a galactic center context. And one thing that Stefan just said is that we know that there were obviously large flares in the past, a few hundred years ago. We know that from X-ray echoes of molecular clouds surrounding the galactic, the very center. And so that gives context, so that lets you expect that there might be particular events happening. At the same time, there's also context for these sources being stellar in nature, and in particular, potentially, as an idea which we like very much, potentially stellar binary mergers. And what I just want to tell you here, I hope that I can maybe give some evidence or some reasons why one could believe that G1 and G2 are indeed very luminous and probably internally heated, and that they are on distinct Keplerian orbits, and that their continuum components show, in one case modest, and in the other case no tidal interaction at all, and so that they are most probably exotic stellar objects. So they are not normal stars, they are not main sequence stars or something. One thing that Stefan said before is that a star doesn't rule the connection between a star and an accretion event is not clear. And we would actually argue that if you have a source that's of stellar nature, you have much more mass there. We know that it's tidally interacting. That is completely undebated. So we know from bracket gamma it's tidally interacting with a black hole. And in terms of accretion, actually, I think it's very attractive that we might have such a large stellar object that is interacting, rather than a gas cloud that, if G1 and G2 are indeed related, has to be stable when it goes through periaps. Well, let me just jump into the data immediately. So that is something that Stefan just showed, and basically he just said that there might be some concerns about the way we subtracted those sources. Just to tell you what we did, so this is data, what you see here from March in 2014, just about the time where we expected periaps to happen for G2. And we took data from March to August, so really trying to bracketing, or to have data covering the periaps passage. And we took L-band and K-band interleaving images. And the reason is that G2 is very confused. Let me see. So this is a position roughly of G2, and you see that there are a lot of sources around. So this is SO2, SO8, and it's also such a star, which is a variable source associated to the accretion onto the black hole. And it's very hard actually to make statements here about G2. So one has to understand actually that these measurements of G2 and G1 are actually the hardest measurements probably done at the Galactic Center, both in spectroscopy but also in the continuum due to the confusion situation. So we took interleaved data in K-band, and we have no detection of G2 in K-band, so we can actually measure the brightness of such a star. And we can infer the brightness in L-band via the spectral index. Now there are a lot of investigations of the spectral index. We at UCLA did very careful ones with very high time cadence and looked at flares. And to our surprise, although we see flares of a factor of 30 with respect to the detection limit, we see that the spectral index is constant, minus 0.6, with very, very minor fluctuations on top of it. And so we use the spectral index to infer that data. It is true that our position that you then finally see in the subtracted image is probably pretty coincident with the position of such a star. But this process of subtracting sources is pretty accurate in terms of shape or photometry, but not so accurate in terms of position of the source. Now, you said, Stefan said, or asked, what might the source be? I think it's pretty clear. If you have a 13.8 magnitude source, which is a pretty bright source there, then you should have been able to track it before if it is another source. So we know there is no other source of this brightness moving into this region. So I think it is it is fair to say that this is a clear G2 detection. I will also maybe later, if I have time, still show a slide about the position. And the interesting part now is not only that you detect G2, but also how you detect it actually. If you subtract another point spread function here at this position, you end up with an empty patch. And what it tells you is that G2 survived in a compact way. So here you see profiles of G2 with comparison to the PSF, in black the PSF, and red the data of G2. And as you see, it beautifully follows the profile of the point spread function. So there is no reason to believe that G2 is extended, and you can derive an upper size limit in a very conservative way. That means you take the PSF, you convolve it with an intrinsic size, which is not a delta function, and then you look what you, if you still can fit the data. And if you do that, you get a 3 sigma level basically as an upper size limit here of 260 AU, corresponding to 32 milliarc seconds. So that's the diameter. That's a very conservative limit, yeah?
When you do that, you're trying to fit the original data or the subtracted data?
The subtracted data.
Like you could have asked, you could have subtracted the extension of this cloud from the Sagittarius star itself.
Once more, sorry?
So the fact that there is some, if this would have been a little bit more extended, you could have got rid of that with the subtraction of Sagittarius star.
Well, that's right, if I would have tweaked it, but actually what I decided is, you know, also the position in the subtracted image, I could have basically tweaked exactly as you say, by removing the sources slightly different and so on. I didn't do that. What I did is I just took the spectral index, the exact position of all those sources we know their orbits, their brightnesses from epochs before, and I subtracted that. So there is no attempt to make it more compact than it is. It is just what comes out if you plug in the numbers that we obtain. So I agree. There's some degree of ambiguity in it, but still, I think the way how it looks, right, how precise it actually looks, is an indication that I didn't do anything very suspicious here. The other thing is that G2 it's constant, so in magnitude, in spite of a change of a factor 10 in distance from the black hole, you can see that it actually simply stays at its magnitude of 13.8. We gave it an error of 0.2 here. And I think that now we did, of course, the same experiment once more in March of 2015. And did the same kind of strategy, subtracted sources here. And in principle, what you see here is that it's very analog. And that is now a year after periapse. You can see here a little bit of a tail, which is consistent with the point source. This source is not detected in K-band, so it's not a known source. Nevertheless, I think it is clear that this component in its core is not broadened or anything. And again, we find a magnitude of 13.6, which is consistent with our findings in the year before. So that means that even a year after periaps, there's no indication that this continuum component has evolved in any way other than following its orbit. Another part of the story is that G2 is not alone. So when you look here at the two color composite from 2006, it's K and L band, and this here is G2. And you see here several red sources in the surrounding of Sagittarius star, in particular this one, which is G1. This is also a very interesting source. It turned out, actually, at the beginning it was believed that it's a hot dust feature at the position of Sagittarius star. But it turned out now, and it was published by Fool et al. 2015, that this feature actually moves also on an orbiter around Sagittarius star. And you see here the sequence. When you have two color composites, it really sticks out as a red object that can easily be identified in every single epoch. And this source, very analog to G2, so it resembles actually G2 in many aspects, has also a bracket gamma line. And if you collapse the cube over 270 kilometers at the position of this line, you get this bracket gamma map of G1. And if you compare that actually to the PSF, then you see that it looks like it's slightly extended in bracket gamma. I think that's only a problem here of our two color images and the way how we show it. We did a photometry, so that's actually I will show that. So what we did is fitting an orbit to G1, and the first thing that you find is G1 is more or less an earlier story of G2. So if you look here at the time passage, it actually went through periaps around 2001.5. So something like 13 years earlier than 12 to 13 years earlier than G2. Interestingly, it is in the same plane as G2, orbital plane, but it's not the same orbit as far as we can tell. So we find a significant difference between the argument of periaps. So the orientation basically of the orbit within this plane is significantly with more than 3 sigma different. And I think that this discrepancy between what Stefan has presented and our data can be explained. Here in blue you see the orbit published in Fool et al. It goes to 2010, and we included epochs till 2015, and our orbit looks significantly different. At 0, 0. Sorry, 0, 0. Yeah. And so our time baseline is 11 years versus 6. Sorry. Oh yeah. Sorry, it's up here. Yeah, it's at the edge. I'm sorry. Yeah. So we measured the photometry, and you can see that there might be a light trend. We didn't find any significance, at least not for a linear trend. It might be something we can discuss, but at least there is not much of variability in the magnitude of G1. And together with M-band data, you can derive, similar to G2, a temperature of a few hundred Kelvin, 400 to 600 Kelvin. Now, there's a unique feature about G1, which is really impressive, and that is it is clearly extended in the early epochs. So here you see an image from 2004, and here next to it a 2D elliptical Gaussian fit to that source, in comparison here the PSF. And the interesting thing is that the semi-major axis lies in the same direction as the direction of motion of the object. And we interpreted this actually because it's so significantly extended as and the fact how this extension is oriented as a sign of tidal interaction of the continuum actually of G1 with the black hole. So now that's not all. It's not only extended in the early epochs, but that actually this extension also shows an evolution. Here you see how the extension within 3 years becomes marginally resolved and then is not anymore resolved. And you can see that also here in the sequence of images from 2004 to 2006. It becomes more and more compact in comparison to the PSF of that epoch. And then from 2009, and here's another example, 2013, it is compact. So that is actually, I think, a very surprising finding that this object can become more compact after being at a size where it clearly tidally interacted with the black hole. And we think that this is already pointing to a higher mass in its center. Now there was the idea or the discussion in the earlier talk of Stefan if there might be a continuum counterpart of this tail structure that can be seen in bracket gamma. And there was the idea that might even point to Iris 16 southwest. So we looked in our data, or I looked in our data in the last days. This is data from 2016. And this is Iris 16 southwest. And basically it's this linear feature here, what Stefan referred to. And you see it's crossing here potentially the mini spiral, and then it's hard to see because of this bright star. But if you go in there and you deconvolve it, and I have to say that one has to be really cautious with this image because the extended structure is resolved in those blobs, and that is an artificial artifact of the deconvolution. But nevertheless, you can see this linear feature, I think, pretty clearly sticking out here, missing Iris 16 southwest and even going much further south than the mini spiral. So I think 6 arc seconds, so 1 arc seconds is 8,000 astronomical units. Yeah. Yeah, I just wanted to show that quickly. Now, about the interpretation, that's a little bit tricky, and of course there is no conclusion you can draw with certainty. But what we would like to say is that G2 is likely a star. And the first argument for it is if you take an optically thick black body and you use the Alban flux you measure, you actually get a radius of 2 astronomical units and a very, very high luminosity of almost 30 solar luminosities. So this is a very, very luminous object, and the question is how can it be so luminous? And so we came up with the idea that that is an indication that it's internally heated, which in contrast to the bracket gamma that most likely is externally heated. And if you now you can do a few thought experiments. First of all, here in this plot, I compare several sizes. You see here the Alban radius limit that I developed from the profile, as I showed before. And you can, of course, also here draw in the black body radius that corresponds to the flux density. And now the question is, we would like to compare, actually, can an object of this size, or will it tidal interact? And you can look at the tidal radius, which here is defined as the radius around the G source, outside which the material is in the influence of the black hole, and inside which is still bound to the G source. And this radius is depending linearly on the distance to the black hole, but we know also the orbit, so we can actually show the tidal radius, or this radius, as a function of time. For this, of course, we need a mass. So let's assume for a moment it is a very simple of main sequence stars, and look at those evolutionary tracks and see that for 29 solar luminosities you get something like 2 solar masses, and you get basically the development of the tidal radius over time and compare that to the black body radius. And what that tells you is that indeed for this kind of black body radius, this object would not much tidally interact, with the exception probably around peri-ups for a very, very short time. Now, of course, it doesn't have to have this mass, but because of the exponent of 1/3, this is not very mass dependent. So I think this is still a valuable comparison. What also is interesting is that of course, the size of such a 2 solar mass star is way smaller than the 2 astronomical units that we derived. So it cannot be a simple star. It has to be something more exotic. We can do that also for G1. And what's interesting here, so those 2 lines are again the tidal radius. One here is for 2 solar masses, and that is for 100 solar masses, just indicating the weak dependence basically of the tidal radius on mass. And here, this is the size development of G1. And you see clearly that during those epochs, G1 had to tidally interact with the black hole. You can also compare that, again, assuming the black body radius to be a representative radius. So for G1, we see it extended for several epochs after periapse, but we have no knowledge what happened before periapse. So if we assume it was there at the black body radius, we can simply compare what would be the kind of tidal interaction. You see that here for G1, you basically expect more tidal interaction than for G2, all assuming that those radii and masses that we assumed here are somewhat representative. So that means we have G2 that is almost not tidally interacting in its continuum component, and G1 that is actually somewhat tidally interacting in its continuum component, but nevertheless becomes more compact after several years after periapse. About the interaction with the accretion, I just wanted to show this shortly, a similar plot Stefan has shown. This is the light curve of such a star combined from VLT and Keck from 2003 to 2013. And just what I want to point out, we put a lot of effort in characterizing the variability and trying to understand how to describe phenomenologically this variability. And we know that's a red noise process. We know the flux density distribution is highly skewed. We can see such a star almost 90% of the time. Only 10% is below the detection limit. And we know it's a continuous process with a characteristic time scale of a few hours, 3 to 10 hours. There is no significant quasi-periodicity or indication of more than one state. We have a very careful analysis of that done in 2014. And there are several correlations claimed between X-ray and sub-millimeter variability to the near-infrared. So we have it very well characterized, and we are well prepared to judge if the variability changed. Up to now, we have no indication in the infrared, and I think that is true for the other wavelengths as well. So very shortly, to conclude, what are these objects? So the question is, can they be stellar binary mergers? That is something that we think is very interesting and that has a galactic center context. First of all, it would be a natural solution for several unsolved questions. That is, for example, the unexpected population of B stars, the lack of giants, or the merging, also that merging stars might create high mass stars in the cluster environment, something we see at the Galactic Center. It would also explain several of the properties that we derived for those objects. The large size, the high luminosity, the temperature of a few hundred Kelvin is consistent with what we know about merged or merging binaries. And then the last point is that merging binaries in the nuclear cluster may yield G2-like objects on highly eccentric coplanar orbits as a consequence of the Kozai-Lidov mechanism. And that is something that is at the moment currently investigated as a possibility by Smedrana Oz at UCLA. So in summary, one can...
appreciate that.
Yeah.
Credit for that. It's mentioned below, but G2 specifically as a merger product was suggested by Smedrana, Bodan, Ipni, and Fabian. So you mentioned it below, but...
Sorry, okay, yeah, it's okay. So in summary, G1 and G2 are exotic objects that most likely are stellar in nature. So G1 and G2 both survived periapse. G1 and G2 are on distinct Keplerian orbits, as we find. And we have constant photometry for both sources. G1 returns additionally to the size after being extended that is compact enough to be unresolved. And so we conclude that these may be candidates for stellar binary mergers. Thank you.
Questions? James?
So both G1 and G2, it seems like go below their tidal rate.
Mm-hmm.
You're saying it only has for a short time, just a very active, that's sort of the definition of a stellar tidal disruption. So I'm wondering, I mean, you're proposing that basically both of these stars are going to be tidally disrupted by Sagittarius A star, rather G1 already has 10 years ago. So in principle, we should see some sort of giant disruption like family from G1.
Mm-hmm.
G1 really buried down below the tidal rate, the factor of
Mm-hmm.
10, right?
Mm-hmm.
So just making sure that that's the implication, I guess.
I think yes, that's the implication. Yeah.
Is it fair to say that G1 is bigger than G2?
Well, that's what you get when you look at the black body radius. And I mean, there are two differences. There's an important difference. We can actually resolve G1 and see it for several epochs. So during that time, it's much larger. Yeah.
Okay, so having this in mind, and also the fact that the radio emission, which was predicted,
Yeah.
which was not observed for G2, is proportional to the So it should be more likely that G1 would emit more radio than G2. So is there any idea, do we know if there was any excess of radio emission around 2001 when the G1 was causing the
I don't know about the radio. I checked the X-rays, and there was, I think, there's no indication for that. Chandra was already online, but about the radio, I don't know. Yeah.